So now we come back to the constituents of matter, where we left off in the sixth lecture. Uh, so we start with the evidence for the muon. Now, Anderson and Neddermeyer were looking at cosmic rays when they interact with the material in a cloud chamber, and they found a component of cosmic radiation that penetrates absorbers, namely sheets of lead of 0.6 centimeter, 1.5 up to 1.5 centimeter, and so on, much more than electrons, because electrons produce a shower in this amount of lead, whereas the muon just went ahead and penetrated it. Protons, for instance, of a similar energy would actually significantly reduce their energy or even stop, given the curvature of the trajectories in a cloud chamber. If you remember, Anderson was the one who actually made the discovery of the positron, again using cosmic rays and a cloud chamber looking at this cosmic radiation in the presence of a magnetic field. So this is of course a common thing in the experiments that many people do, including Anderson, which he did. So you, given the curvature, then you can tell the momentum of that charged particle. So the track thickness, which tells you about the dE by dx, the stopping power, or how much energy it loses in a unit distance, its length and its curvature in a transverse magnetic field of between 4 and 8 kilogauss are the observables. The meson, this name is actually due to Homi Bhabha, because it was earlier believed, it was thought to be the carrier of the strong interaction, and was called a mesotron. So Homi Bhabha shortened it, and he says linguistically it is much better if you call it the meson. And this was thought to be the particle that was proposed by Yukawa in connection with the strong interaction that holds protons and neutrons together in a nucleus. Yukawa had, and we will come to that in a subsequent slide, he had estimated the mass of this particle that is responsible for the strong interaction to be of the order of 100 times the electron mass. However, it turned out that this was a mistake, and what Anderson and Neddermeyer were seeing was not actually this particle proposed by Yukawa, but a heavier cousin of the electron. This mistake was realized. It was then called the mu meson. Of course, later it was simplified further, and it's now known as the muon. It does not interact strongly with matter. And given below here are some of the key references. Neddermeyer, Anderson, they first reported in a conference in 1934, and they wrote up the paper. In fact, two papers, Fizrev in 1936 and 1938, and the article was titled "Cosmic Ray Particles of Intermediate Mass." A similar piece of work was done independently by Croussard and Prince Ranguet and reported in Compte Rendu, the French group, in 1937. Okay, now we come to the pion. This is having a similar mass as the mu meson, somewhat heavier, and it was discovered again in cosmic ray interactions with matter. So the photograph here is one of Powell, to whom this discovery is attributed, but somewhat earlier to the work of Powell, D.M. Bose and Biba Chowdhury in Calcutta, they actually published, they carried out an experiment and published evidence for a mesotron, as it was known at that time, of mass about 150, let's say, to 260 times the electronic mass from cosmic ray interactions in a Ilford photographic plate. And they did this experiment at low altitudes and high altitudes because they had access to the Himalayan range. And so near Darjeeling, they found sites where they placed this at about 3,660 meters, and they found evidence for this a mesotron of mass in this limit. So this was kind of the first indication that we have seen a mesotron. Also from its interactions with once it is produced, its interactions with other nuclei, because it's a strongly interacting particle. However, the large band in which this mass of this mesotron lay was improved upon significantly by experiments carried out by Powell's group in Britain. And what they used was, they didn't have access to, of course, high mountains in Britain. So they used balloons which could go even higher up, of the order of about 10,000 meters and so on. And this was used very effectively by them a few years later, 7-8 years later, to measure the meson mass to a better accuracy and with more confidence of 240 plus minus 50 times the electronic mass. They also, in some of their pictures, and one of them is shown here, found evidence for pion to muon decay and then muon to electron decay. Okay. So, for instance, this picture, which is I think from his Nobel lecture, a kaon comes in from the cosmic ray. It interacts with the nucleus here. It produces a pair of pi pluses and a pi minus. And then this pi minus interacts again with something and produces again a couple of particles. And this is the scale of the length scale that is given here. It is of the order of, this is of the order of 30 micrometers. So the references are given here. This reference is of D.M. Bose and Biva Chaudhary. This is the Nature paper in 1941. So they predated the work of Powell and Occhiolini by about 6 years. However, they, as I said already, the evidence was, I mean, this was an indication. So they didn't have very definitive evidence, and that definitive evidence came from the work of Powell. The mesotron, this mesotron which was seen, later named the pion, interacted strongly with matter. It was seen that when it is, after it is produced, it interacts in the same emulsion, and it was identified as the particle responsible for the strong nuclear force through exchange between nucleons. Nucleons is just a jargon for neutrons or protons in the nucleus. From the short range of the nucleon-nucleon interaction, of course, its mass was inferred by Yukawa. This was done in 1935. This is the original paper, the Proceedings of the Physico-Mathematical Society of Japan, 1935. So he kind of modeled it on the basis of the photon exchange between two charged objects, which is responsible for the electric force. In this case, of course, the nucleon-nucleon interaction is not infinite range, which is so for the case of the electromagnetic interaction, since the photon mass is 0. But in this case, the nucleon-nucleon interaction is short range, it dies exponentially, in fact, as we know now. So he inferred the magnitude of this mass from a very simple argument using the Heisenberg uncertainty principle. So what is that? How did he do that? So let's say the typical distance scales are r nuclear, and the mass of the pion is m pi c squared actually. So the Heisenberg uncertainty principle allows for fluctuations in the energy and time, provided delta E delta t is of the order of or greater than h cross. Since you have a distance which is typically of the order of magnitude estimate is velocity of light times the uncertainty in the time. So then delta E, which is you want to have a pion produced virtually, which will get exchanged between these two nucleons, then this product R nucleus times m pi c squared is of the order of h cross c, which is as we saw in about 200 MeV Fermi. So for R nucleus of the order of 1.4 Fermi, m pi c squared comes out to be 140 MeV, which is in fact is the mass of the pion roughly that we know now. Of course, if you take R to be 1 Fermi, then this m pi c squared, you can still get a correct order of magnitude. Then you get this to be about 200 MeV, which is what Yukawa estimated. Now we come to the neutrino, which was something that was proposed by Pauli in connection with a very serious problem that was encountered by researchers in the case of beta decay. It was found, of course, quantum mechanics had been born in 1925 when energy levels are discrete and so on. So if you have a beta decaying atom, it has a certain discrete energy, and suppose it decays by beta emission, goes to the ground state of the daughter nucleus, that also has a definite energy, and therefore the beta has to be having a definite energy. So this is shown here. For instance, suppose you have a carbon 14 decaying into nitrogen 14 and a beta, then the beta has to, since it's a two-body decay, you can of course conserve momentum, and if you have to conserve energy, the beta being much lighter than 14 nitrogen, it carries away most of the available energy, the so-called Q value or the energy released in the beta decay, and so you get a peak. Suppose were you to plot the differential energy spectrum dN by dE beta versus E beta, you should get a peak here. Okay, this blue peak, of course, is shown to be broad because you will have a finite energy resolution. Otherwise, if you had infinitely good energy resolution, this should just have been a delta function. It should just have been a single line here. So this is the case of two-body decay. And I'm jumping the gun, but let me just say that okay, or maybe I should go to the next slide. I can come back to this slide again. So, however, the observed spectrum of betas experimentally was that it was continuous, right from 0 to the maximum energy to the Q value or the energy released in beta decay. So, it was a continuous spectrum as was shown in this previous slide. So, this is the problem, that why is it sometimes having small energy, sometimes medium energy, and sometimes the maximum energy possible, but not a definite discrete value which is given by the energy release in this beta decay process. So Pauli made this proposal of a new neutral particle. He said it has to be neutron-like particle, and could then explain the continuous nature of the beta energy spectrum. Now, this proposal never actually got published by him because he thought that this was a very odd way of solving a problem. However, this is the way you can solve this beta decay problem. So he wrote a letter to the organizers of a conference where he was supposed to give a talk. Instead, he went to a ball, and so he wrote to the people who were organizing and participating in this conference. Dear radioactive, so let me read it out, very interesting. Dear radioactive ladies and gentlemen, how, so he says a few things at the beginning, and then he says how, because of the wrong statistics of nitrogen and lithium-6 nuclei, which have integral spins, and the continuous beta spectrum, I have hit upon a desperate remedy to save the exchange theorem of statistics and the law of conservation of energy. We will come back to that. What does he mean exactly by that? Namely, the possibility that there could exist in nuclei electrically neutral particles. So at that time it was believed that the particle, if it has to come out, it has to exist already, just like you have electrons in an atom, and then they can be kicked out by interacting with a photon, as in the photoelectric effect or Compton effect and so on. So these electrically neutral particles have to exist in the nuclei that I wish to call neutrons, which have, by the way, the neutron was only discovered in 1932 by Chadwick. So it was okay if he called it the neutron, which have spin half and obey the exclusion principle. This is the so-called Pauli exclusion principle that he is referring to, and which further differ from light quanta in that they do not travel with the velocity of light. So he already anticipated that this in general could have a mass and perhaps a small mass, because the mass of the neutron should be of the same order of magnitude as the electron mass. In any event, not even if it is larger than the electron mass, it cannot be larger than 0.1% of the proton mass. So this was his proposal, and as I said, he was not very happy with this possibility, but he said, this is all that I can do to solve this problem. So he called it a desperate remedy. Okay. So, the little neutron was later named the neutrino by Eduardo Amaldi. It is often attributed to Fermi, but it is actually Amaldi who proposed this. And then Fermi continued with this name, neutrino. Uh, so, Fermi constructed the first quantum field theory for weak interactions. Of course, the very first quantum field theory was that of quantum electrodynamics, which Dirac had written down. Uh, so Fermi did this in 1935. He modeled the quantum field theory for weak interactions on the field theory for electrodynamics, quantum electrodynamics. Uh, Surprisingly, this paper was actually rejected by Nature, which was the well-known journal of that day. Uh, Later on, of course, editors have regretted this decision, that they actually rejected the paper, which was a seminal paper of Fermi. Fermi, in his usual style, being a very practical person, he submitted it to an Italian journal, and of course it got published. The other development that took place a little before this was that the neutrino interaction cross section was calculated, and we have seen this in the earlier lecture, using just dimensional arguments and some numbers associated with beta decay to be about 10 to the minus 44 square centimeters. And interestingly, Bethe and Piles concluded that therefore this particle is impossible to detect, because it had a cross section which was 19 orders of magnitude smaller than a typical nuclear cross section, which is of the order of a barn, and this cross section was 10 to the minus 19 barns. So they said this is impossible to detect. Of course, happily they were proven wrong, and in fact even Bethe was happy that Bethe and Piles were happy that they were proven wrong. Bruno Pontecorvo, again, who worked in Fermi's group in Rome in the early days, in the 20s and 30s, he first proposed a radiochemical detector, radiochemical experiment to detect the neutrino. So a neutrino comes in, it interacts with the chlorine. Actually, there is a mistake here. I should correct it perhaps. It should just be the electron type of neutrino, not the antineutrino. And that interacts, he proposed, with 37 chlorine to give you an electron and 37 argon. Now, 37 argon is a nucleus which is radioactive. It has a half-life of about 35 days. So, you have a huge, let's say, a tank which contains a chlorine compound. Chlorine 37 is about a quarter of the total amount of chlorine that there is. So, you have two isotopes, 35 and 37 chlorine, and chlorine 37 forms about a quarter of that, and you produce argon. So, then you separate out this argon, and this was elaborated by other people including Alvarez and so on. So, this was a proposal when he was in Chalk River. Later he moved to the USSR. He never actually carried out this experiment. In fact, Ray Davis carried out such an experiment using a carbon tetrachloride as a detector of these neutrinos at a reactor, at a nuclear reactor. But he got a negative result. This was done in 1955. He got a negative result because, of course, and he said so in the paper that was published, that the electron neutrino is different from the electron antineutrino. Okay, so what is needed in this reaction is that you have to have a neutrino, and nuclear reactors produce antineutrinos. So, of course, that doesn't allow this particular reaction to go through, and he did not observe any argon 37s above background. So, he got a negative result. And these are the players: Enrico Fermi, Hans Bethe and Rudolf Piles, Bruno Pontecorvo and Ray Davis. Let me also say that in those days, things were very different. People were much more accommodative and friendly. So, Davis actually wrote to Bruno Pontecorvo asking if he was still interested in doing this experiment of detecting neutrinos. So he was, after this negative result, he was interested in carrying out an experiment to measure the solar neutrinos. So he wrote to Pontecorvo and he said, "Are you interested in doing this experiment?" And Pontecorvo said, "No, I am not going to do this experiment." By that time, of course, he was on the way to moving to the USSR, the then USSR. And so Davis continued with Bacall to propose such a detector for solar neutrinos. Of course, we will have a lot to say about that in a subsequent talk. Okay, so coming back to the neutrino, the first detection of the antineutrino was done by an experiment led by Reines and Cohen, Fred Reines and Clyde Cohen. In 1956, they reported the detection in a paper which was actually quoted in the Nobel Prize, which Fred Reines got in 1995. So what they did was they used, first of all, a reactor, a fission-based reactor, nuclear reactor, to as a source of neutrinos. So actually, this should be anti-neutrino here. I think there is a typo here. This should be the anti-neutrino. So let me correct it right away. So the antineutrino interacts with the proton, let's say, to produce a positron and a neutron, and the proton is part of water molecule. So they designed a detector which had layers of water and liquid scintillators, and of course outside of that they had veto counters and so on. So a neutrino comes in from the reactor here. It interacts with proton in the water molecule. So this water has dissolved in it cadmium chloride. So the neutron that is produced on the scale of tens of microseconds thermalizes, then gets captured by cadmium. It produces high energy 2 or 3 gamma rays, which then get detected by liquid scintillator, in between which this water layer is sandwiched. The positron, on the other hand, annihilates with one of the electrons in water and produces 2 photons of 511 keV back to back. They also get detected in the liquid scintillator, these two parts. So as I said already, the water is sandwiched, and then there are several of these layers. Okay, so the signal for this, the experimental signature for this reaction to take place, is that you have a prompt signal from the two 511 keV gamma rays that come as a result of the annihilation of the positron, the two 511 keV gamma rays, and a delayed neutron capture which gives rise to 2 or 3 gamma rays, okay, whose sum energy is of the order of 8 MeV, of the order of. Okay. Of course, they could put a higher threshold. This was the use of that, because on the average then these gamma rays would carry an energy of 2 to 3 MeV. So they could put a high threshold on this, on the Compton spectrum of these gamma rays in the liquid scintillator. So they did initially this experiment at the 300 megawatt thermal Hanford reactor, and then went and did this at the 700 megawatt Savannah reactor in the US, where the signal to background was of the order of 3, and they in fact from an estimate of the number of neutrinos that you have per second coming out of the core of the reactor, you can in fact make an estimate of the cross section, and this turns out in their experiment to be of the order of 6 times 10 to the minus 44 centimeter square. So this is the same order of magnitude as the estimate of Bethe and Piles. Okay, so let's come now to the discovery of the muon type of neutrino. Now, of course, the muon was discovered in the 30s. So Pontecorvo and other physicists said that, just as there is a neutrino associated with beta decay, there should be a neutrino associated with pion decay. The pion decays through the weak interaction. So, because of course, how do you know that it's a weak interaction? It has a rather long half-life, tens of nanoseconds. On the other hand, were it to be a strong decay, it would be that this lifetime is of the order of 10 to the minus 20 or 10 to the minus 22 seconds. So, this has to be a weak process, and if this is so, then the pion decays through a two-body decay to the same charge muon and a neutrino or antineutrino, as the case may be. Similarly, the kaon, which is a strange meson, also would decay into a muon. For instance, one of the decay modes would be a muon and a neutrino. And these are the lifetimes of the pion, the muon and the kaon. Pion is 26 nanoseconds, mu is the longest lived, is the lightest meson or the lightest lepton after the electron, and so it has a lifetime of 2.2 microseconds. The kaon is heavier, and therefore it has more decay mode, so it decays, but of course it has a strange quark, so that slightly slows down the the decay process. Nevertheless, it has a lifetime which is of the order of half of the pion lifetime. So, this was proposed, the experiment to look at to search for the muon type of neutrino was proposed by Schwartz in the east coast of the US, and he got his main collaborators were Steinberger and Leon Lederman. So, they proposed an experiment at the Brookhaven National Lab, which then had the high energy accelerator called the AGS, alternating gradient synchrotron, which produced of the order of 20 MeV protons, 20 GeV protons. So, this should be GeV. Let me correct that. This should be GeV protons. And so, the idea was that you produce pions, which are strongly interacting particles. So, in a high energy GeV or 10 GeV proton interaction with the nucleus, you get lots of pions, and then these pions, if they are low energy, they of course stop and then decay, but many of them are high energy, so they decay in flight to a muon and the muon type of neutrino or antineutrino, as the case may be, depending on the charge of the pion. Similarly, the Ks also produce neutrinos. Now, of course, we will come to that in the next slide. Then, because the neutrino interaction cross section is very small, of course, you require a lot of shielding to stop some of the high energy particles that are produced when the proton interacts with the beryllium target. And so, this was, so there is a huge arrangement of shielding material. So, you can see that the vertical lines, they represent concrete. So, this is a huge amount of concrete in between to stop some of the high energy particles that are produced upstream of the target. Then you have steel, which is basically 13.5 meter of steel shielding, which is from the deck plates of a dismantled cruiser ship. And before these neutrinos will impinge on a detector, which consists of a 10-ton aluminum spark chamber, which is 21 meters from the target. So, this shielding stops muons of either charge. Okay. The cosmic background, of course, which is from the top, that is of course producing also some single track events. So, they produce about, in this case, the final data showed that they had about 5 such single track events. However, 29 of these single track events were due to neutrinos. So, the charge current interactions of nu mu or nu e result in muons or electrons, and so in the case of electrons, you produce a electromagnetic shower, which is a very short distance shower, whereas the muon is a very penetrating particle. I mean, to give an analogy, it's like a bull in a china shop. So, it just keeps on going till it stops. So, there were very few shower events seen, so which means that this was a nu mu and not a nu e that came from this interaction. Okay. And this is the discovery paper done by et al. Fizerev et al. In 1962. And this is what fetched Steinberger, Lederman and Schwartz the Nobel Prize. So, the energy spectrum of neutrinos from the 15 GeV proton beryllium interaction is like this here. So, you see the number of neutrinos per GeV per square centimeter per 10 to the 11 protons impinging on the target ranges from about 1500 to much smaller numbers over a span of about 0.4 GeV to about effectively to about 1.5 GeV or so. From the kaons, since the K is more massive, then it produces relatively higher energy neutrinos, and so this starts out at about 0.6 GeV and goes on up to about 3 GeV. So the detector consists of, as I said, spark chambers, 10 of them, one above this median plane and 5 below the median plane, so 5 above, 5 below, and there are trigger counters here which are denoted by A. It may be a little hard to see that. So there are 5 such trigger counters in the top section, and similarly 5 such in the bottom section. There, of course, this is a side view, so the detector is pretty large. Each of them, as I said, is about a ton, and the spark chamber is something that actually gives a spark when a charged particle moves through this spark chamber. So there are high voltage applied in the spark chamber and a gas in between. So this leads to a spark, and that's why it's called a spark counter. So BCD, which is here, B, C on top and D, they are cosmic veto counters. So if a cosmic ray particle comes from the sky from top, then this is detected, or even from the side here it gets detected, and you can choose to tag this event as a cosmic ray event. So you don't consider that event as something of interest for neutrinos produced from the accelerator. Of course, this spark chamber is also viewed by 4 stereo cameras, so that you can tell spatially where this event occurred. Okay, so in summary now, we have seen how the muon and pion were discovered in cosmic ray experiments. We have seen how the electron antineutrino was discovered in a nuclear reactor experiment, and its cousin, the muon neutrino, was discovered in an accelerator based experiment. Okay, so thank you.